Should we start? Wait, did I press Alt? No. How dare you? Yeah, I pressed all the buttons, so this should record. Welcome back. Today I will talk about the project, but I want to do this at the very end. We'll talk about collisions and contact and implicit constraints first. And since it's been a while, you probably don't even remember who I am after not seeing me for, 3 weeks, 4 weeks. I thought it makes sense to start with a bit of a recap. And what we did was we started talking about loops. And the way we model loops was basically through this idea that then can also be applied to other situations by basically separating the constraints that we have in some that we treat as explicit constraints and some that we treat as implicit constraints. The way we write the explicit constraints is that some position of a body can be interpreted as a function or can be computed as a function of a set of generalized coordinates. And the way we look at implicit constraints is that we say if I know the Cartesian coordinates of a body, I can constrain them through some equation to something that is being equal to 0. And this thing that is being equal to 0, we looked at this more closely and said this is our constraint violation. If it's non-zero, the constraint is violated. That's not what we want. But this is what I've drawn here. The constraint is violated. So the C, this contact constraint violation, is non-zero in the picture. And putting this together, right, since this is a function of x and x is a function of q, I can define a new additional implicit constraint that says this contact distance is directly a function of my generalized coordinates q. This has to hold on position level, being equal to 0, on velocity level, and on acceleration level, and basically gives me a linear constraint on our possible q double dots, on our possible accelerations. So I cannot choose my q double dots freely, as I can do in a purely explicit constraint, but I have these additional implicit constraints that reduce the number of degrees of freedom. Physically, this is happening because there are constraint forces that prevent the constraint from being disassembled. And these constraint forces, we call them lambda. The constraint forces are projected into the generalized coordinates using our standard Jacobi transpose mapping, where the Jacobian, the J lambda, is of course the same Jacobian that we just saw in the kinematics, which means I can simply add those constraints to my, or those constraint forces to my canonical form of the equations of motion. So there's an additional term because, without this would be the equation of motion without the implicit constraint. And from a dynamics perspective, we just say it's something that produces forces. And these forces are projected in my generalized coordinates into my Q space. And then I have additionally here these constraints on acceleration level. So I have a differential algebraic equation, a DAE, which I can solve because I have taken 2 derivatives of my constraint equation. So this was originally given on position level. I took 2 time derivatives, got it on acceleration level, and then ended up basically with this form here, where I now can simultaneously solve for my accelerations and my constraint forces. And I said at the beginning, right, this is what we did here to deal with loop joints, but you may have other situations where you want to model a particular joint as an implicit constraint rather than an explicit constraint, and then the same process, of course, would work, right? To treat some of the coordinates or some of the constraints with an explicit constraint, derive the equations of motion for that subsystem without the additional constraint, and then add your additional constraint here. In terms of what do we need to compute if we are implementing this, the 2 things that are new is this constraint Jacobian, J lambda, and are the bias acceleration sigma lambda. This is what you have to compute if you want to implement a simulation with such an implicit constraint. And this is where I typically tend to get a little bit lazy and start thinking about how can I get these quantities with the framework that I have already created. And we had the simulation here of our little passive dynamic, of our little legged robot that was standing there. I run the simulation that you see what's happening, where we have a floating base and then 2 loop joints at the 2 feet. And basically, the 2 loop joints that we had were rotational joints. We just said we have point contact, so the feet, they cannot move left and right, they cannot move up and down, they can just rotate. So essentially, I have, in terms of a joint type, I have a rotational joint there. The way we implemented this, and there's actually 2 versions, you will get this on Thursday with the examples for our last exercise, for exercise 7. The version that I showed you before the break modeled these additional implicit rotational joints through massless bodies that we called the feet. We had a body for the right foot and a body for the left foot. And these bodies, they don't carry any mass or inertia, so they don't change the dynamics. They were just a means for me to get a additional coordinate system and information about where that center of gravity of this virtual body or the zero mass body would be. So I can now use my standard kinematic framework, which is computing COG positions and COG velocities, but I misuse a body that has no mass to just place that almost like a sensor or like a coordinate system in this particular point. And then I know that my constraint is that point is not allowed to move. And this is what I will see in my constraint Jacobian. So we had this function here that we called getConstrainedTerms. But basically, all we have to do is get the Jacobian of this particular foot point, which is not allowed to move left or right. So I took the first 2 columns of my, left and right and up and down, so the planar constraint. So I take the first 2 columns of the Jacobians associated with this foot point. And then I do a coordinate transformation because I want these constraint violations be expressed in horizontal and vertical direction. Only reason is because then also the contact forces, or the constraint forces, will be expressed in horizontal and vertical direction. And if later on I'm, for example, interested in the question, will this slip? Right? Is friction large enough? If I have a horizontal and vertical component, I can basically look at what coefficient of friction I would need to keep the foot in place. And that's why I do here this conversion into inertial coordinates. Otherwise, it doesn't matter. The sigma lambda is simply the bias acceleration of these contact points, of the foot points. Here I just look at the acceleration, but you all saw this last Thursday. Whenever in my framework I get an acceleration, it typically means bias acceleration because I computed this through my call of recursive forward kinematics with q double dot being set to 0. So these are bias accelerations. And then I update those with the Baumgartner stabilization terms, and this would be my j lambda and my sigma lambda. Now, you could argue this is a bit of a hack, right? And the only reason why this works so well is because I have pin joints or rotational joints, and I have contact with a stationary object. So all I'm basically saying with these constraints is keep that particular point stationary. Right? That is how I implemented this. And it's not a very generic way of thinking about this problem, because it would require you to, in a sense, for each potential loop joint that you have, right? Maybe at some point your loop joint is going to be a slider. You would have to come up with some way of hacking our framework to get these expressions through some coordinate system. So the question is a little bit, is there a more structured way of doing this? And in fact, there is. Because of what we did so far was basically, I start at ground. Here's my virtual 3 degree of freedom joint. I have an upper leg segment, and I have a lower leg segment. And then I have a point contact here, which directly connects to ground. And I said, this is going to be my loop joint. And then I had to recreate in my implicit constraint, basically what you see here are equations for a rotational joint. I could, instead of breaking the loop apart here, I could break the loop apart here. Which means what I do here, I add a rotational joint. And in this rotational joint, I add a tiny bit of ground to which I do not assign a mass. And then I say, I have a joint between here and here, which is a zero motion joint. And I cut my loop between these zero motion joints, or between these two ground objects at the zero motion point, which means I get a new constraint, right? Where I have to implicitly constrain ground not to move against ground. And you kind of see that this is something that can be used in a very generic sense, because I always basically, instead of breaking my loop at a joint, I break the loop in a body, in this case ground. And to then reassemble this with an implicit constraint, I have the same type of constraints. It's always going to be a rigid connection that I'm creating through my implicit constraint. And I have implemented this as well in our examples for the next exercise. It means that my system is set up a little bit differently. So here, maybe I'll show you this first. When we set up the system, we had these bodies, and I had a left foot. Sorry, I'm already at the joint. So I had a left foot and a right foot. And the left foot and the right foot were connected to the corresponding shank, so this element here, through a generic joint. So here I basically had the rigid connection, which means I was able to use my foot as a coordinate system attached to my lower leg, to my shank. Now here I do this slightly different. I have segments that I don't call the foot, but the ground on the right and the ground on the left leg. Again, they have zero mass, so they're purely virtual. But now they are connected to the shank with a rotational joint. So this is exactly this joint. It's a rotational joint that connects this tiny bit of ground under the right foot to the lower leg, to the shank. And then, of course, the same on the left leg. So here I very explicitly use the framework that we have to model a rotational joint. And you can kind of see the advantage, because if this was a rolling contact joint, I could just go ahead and use the rolling contact joint from our framework. Whereas doing a rolling contact joint through this other process, or an implicit rolling contact joint, would be very, very difficult. And then all we have to do in our constraints is to say these two bodies are not moving relative to each other. So there's no relative motion, translational and rotational. So my constraint space is now 6-dimensional. I have 3 translations, 3 rotations. And the rotations, the translations, of course, I get from my, from my translational Jacobian. And you see here the difference, right? Translational Jacobian on ground R, so my little ground element on the right foot, minus translational Jacobian on the large ground, the actual ground. And this expression, or this Jacobian, gives me the velocity of ground. just 0 in this case, but I wanted to keep it generic because could have cut here as well, and then this velocity would not be 0, right? And this is the velocity of this little ground segment. And then I'm basically saying with this minus sign, those two have to be equal because the difference in velocities, that's my constraint violation velocity, that has to be equal to 0. And then I do the same with the rotational Jacobians, so for angular velocities, and I do the same, of course, here for the left foot. So in total, I get here 12 constraints. In exactly the same fashion, I compute my bias acceleration, so acceleration of the large ground minus acceleration of the small ground has to be equal to 0, right? And whatever difference I get is here a bias acceleration because I computed this A with Q double dot set to 0, and then the same, of course, for angular accelerations. So this is now very standard, right? It's basically the implicit constraint that corresponds to a rigid connection between two bodies, and that is always going to be the same, right? So whenever you think about where do I put my loop joint, this always works. Set up my Baumgarten stabilization, and then comes a bit of a pitfall. And you see here that of these 12 constraints, right? Basically, when I have a 12 by NQ constrained Jacobian, I have 12 constraints. I don't use all of them. I just pick a few. 1, 2, 6, 7, 8, and 12. Why those?
The first two are the translational motions, and the sixth is the rotation around its third axis.
Mm-hmm. Exactly. So sorry, you just said the keyword I was looking for. The issue that we have here is that we have a planar problem, right? Everything is in a plane. And so I only need the constraints in a plane. So I do x and y and rotation about the third axis for the left body. And then 7, 8, and 12 is the same for, sorry, this was, I think the first is right leg, and then the second, the last three, second half is the left leg. I only need to select them because I have a purely planar problem. It actually turns out that if I set up all the other constraints, my system doesn't really know what to do. Because it's basically saying there's a constraint that your foot cannot move left. But there's no Q, right? There's no generalized coordinate that allows my legged system to move left, because the way I set it up, everything here is planar. So this contact point, there's no way it can go in this direction. No choice of Q is ever going to make this go in this direction. Now, if I now add an additional constraint that says this point is not allowed to go in this direction, MATLAB in the background tries, or our equations that we have, try to figure out a Q double dot that allows it to compensate for any motion in this direction, which doesn't work because there's no Q's. So we are basically looking at this idea of dependent constraints, that the constraints that I'm setting up here and the constraints that are given through the Q are dependent. They're not independent, and this can give you numerical issues. And this is why I selected only the constraints that are in our XY plane. The text says you cannot, if you don't want to do this, the issue you can, if you don't want to do this, you can use a pseudo inverse here. Basically, what happens is I'm adding, well, you can think about this, right? How many Q's do I have in the system? 1, 2, 3, 4, 5. And then down here, I'm adding 6 constraints. That doesn't work, right? It works because some of the constraints that I'm adding will never be violated, right? They're dependent constraints. So even if I write 6, I'm just actually only adding 3. But you don't see this in the equation. So if you were going to invert this equation, you will not have enough q's to numerically satisfy all the constraints. So you would have to work, for example, with a pseudo-inverse. That's one drawback. The other drawback is if I want to remove the constraint. We saw this also in the example that in this implementation, it was very simple to say, I only want the first 2 constraints to be active. And all I had to do is say, I just pick the first 2 rows of my constraint Jacobian and the first 2 rows of my bias accelerations, and everything else stays the same. If I do this here, of course, I could do this, right? I could pick the first 3 constraints if I just want to be on the left foot. The issue that I will get is that then here I have a segment that has 0 mass. And that can spin freely in this direction, either forward or backwards, right? There's no mass associated to it. So physically, or from a physics perspective, we cannot compute an acceleration. It can have any acceleration around this axis. It's not going to change anything. And this, again, will show up as a weird singularity in this mass matrix, right? In one case, this Jacobian is getting singular if we add too many constraints. In the other case, this mass matrix is getting singular. It will have a 0 entry somewhere. You can still solve this with a pseudo-inverse. You would just sort of get the minimal norm q double dots, which means that likely the acceleration about this axis is being set to 0, even though in terms of the equation, it can take on any value. You have questions about this. I know it was quick, bit of a recap, but also showing you these 2 approaches. And you will understand this a little bit better next week when we do this in an exercise, right? Our last exercise is going to be modeling or simulating a system that has such a loop, such implicit constraints. But sort of in terms of theory, in terms of sort of the general idea, whether I cut my loop joint, what does that mean in terms of constraints? Do you have any questions?
Yeah, for
yes?
example, when the left foot is lifted off the ground, would you still consider it a joint?
You would not enforce the loop, right? So I would still have the joint here, but you would not have the rigid connection from this ground to that ground.
So it's still a rotational joint when it's lifted up the ground.
Yes, and this is sort of the problem because this thing can rotate freely about this joint axis if it's in the air, but there's no mass associated with it. So it can rotate with any acceleration. There's no, of course, there's also no torque applied, but no torque and no mass means any acceleration is possible, and this is why you cannot directly invert the mass matrix.
Can you add a condition that says that if it's lifted off the ground, it will be considered as a body instead of a joint?
You have both. You have the shank, then you have a joint, and then I have a little body that I call the right ground. And that little body, if it's lifted off the ground, then is attached to the shank and can rotate. I could, in theory, I could give it some mass. But that then, of course, would change the dynamics, right? It would be like you're moving around your foot and you actually have a piece of ground stuck to it. So I wouldn't do that. I'm not sure if I'm answering your question there.
No, I meant that if it's lifted off the ground, you can remove the joint altogether. Would that be possible?
You could, but that would mean basically setting up an entire new simulation. Right? And you could do this and say, I have equations of motion for the foot on the ground, and I have equations of motion for the foot in the air, of course, with different numbers of degrees of freedom. And you just need basically to map. But of course, this is much more comfortable, right? Just to say I add or remove a constraint is much quicker than saying I compute a totally new set of equations of motion. Maybe we should talk afterwards, because I think I don't understand your question. And Let's see, are there any other questions? No? Then let's move on to our next topic, which now has to do with exactly this transition, right? If I just have a slider crank mechanism, which has a loop joint, I would model it this way. I would never change my constraints. But if I think about, for example, a walking robot or any robot that manipulates something, you have contacts that go into effect and come out of effect, right? When I'm walking, foot is in the air, I have a different system than foot is on the ground, right? I have more constraints, my dynamics inherently change. And this is often represented by what we called a unilateral constraint, where I can have these two situations of the contact being open, in which case the constraint isn't really there, and the contact being closed, in which I, in this case, could treat it as a simple rolling contact joint. And at this point, we would be able to model both of these situations using, of course, using different structures or using two different models. This idea of unilateral constraints can become very complex very quickly. There's actually an entire lecture that's called non-smooth dynamics, which only deals, right, one entire term just deals with this type of problem. So here I'm going to show you the short version, show you some ideas, and to do that I make a few assumptions that are not 100% correct, but are actually widely used in the field of robotics. And the assumption that I want to make here is that we have infinite friction. So we have a contact with infinite friction. And in fact, all the cases that we're going to look at are either infinite friction or zero friction, because everything in between is a little bit more complicated. What does that mean? When we have infinite friction, we basically have a rolling contact constraint on the right-hand side. And the way I would formulate that is by saying that I have some constraint violation velocity and some constraint violation acceleration that have to be equal to 0. This is how we would model this. And this is, by the way, looking ahead a little bit, not something that automatically follows from the fact that you have infinite friction. Sounds a little bit counterintuitive, but having infinite friction doesn't mean that there's no sliding. You can have sliding with infinite friction, because your normal force can tend towards 0, right? And then 0 times a coefficient of friction that is infinite can still give you some finite tangential force. But we ignore this for the moment. So here we assume we have infinite friction and immediately translate this into our contact is not sliding. And of course, it's also not moving down through the ground. And we're also at this point, when we say the contact is closed, we assume we have no liftoff. And then there's going to be a constraint force, a lambda, a contact force that ensures that constraint. And I'm going to write here lambda is equal to question mark, which doesn't mean we cannot compute it, right? I just showed you how to compute it, but it's not given a priori. It follows from the dynamics. The reason why I want to write it this way is because on the left-hand side, we kind of have the opposite situation, where I know that there is no contact, which basically means the contact force, the lambda, is going to be 0 here. But the constraint violation velocity and acceleration. Those we don't know, right? We can compute them. We just do forward dynamics and compute the motion of the leg, and then we know the motion of the foot, and from that we can compute the constraint violation velocities. So we see a bit of a dual structure here, right? Here I know the force is 0. Here I know the acceleration is 0. And the other quantity basically follows from our dynamic formulations. The way we're gonna compute this is through this equation, and by basically just picking the rows of our Jacobian J lambda that correspond to active constraints. This is what I just showed you in the implementation. So we set our constraint Jacobians, J lambda and sigma lambda, such that my constraint space only includes the active constraints. So far, nothing new, right? I just talked about, I talk about a unilateral constraint, but the way I presented it so far is as there's two cases. Either you're not in contact, then you're unconstrained, or you're in contact, then you just set up your constraint Jacobian and use the standard process that we just looked at to resolve the loop joint. The interesting bit, of course, is now that we can transition between these two cases. And maybe I start with the transition from left to right. What would trigger this transition? When do I go from open contact to close contact? When I detect the collision, but how would I here numerically or mathematically detect the collision? Well, I can look at one part of my constraint violation, and this is here the perpendicular distance to the ground. I will call this C perpendicular. That C perpendicular, because I have a unilateral constraint, has to be larger than 0. This is why we also would call this an inequality constraint, right? We talked about equality and inequality constraints, and here I'm basically showing you not the entire thing, but this perpendicular distance that is not equal to 0, but that has to be larger to 0, or actually larger or equal to 0, because here on the right-hand side, of course, that contact distance or that perpendicular contact violation has to be equal to 0, right? Overall, between the two cases, we get sort of this inequality. This distance should be larger or equal to 0. In the left case, it's strictly larger than 0. In the right case, it is equal to 0. And then, of course, we get the transition when I basically run my forward dynamic simulation on the left. I monitor my C perpendicular, and as soon as that becomes 0, and if it continues to get smaller, so if it is strictly smaller than 0, this is to avoid what we would call grazing, where you basically just barely touch the ground and then move away again. Here we say I really want to move into the ground, so the distance becomes 0 and my velocity is negative, so I'm still moving into the ground. If I would not do anything, my foot would now move through the ground, right? And this is what we want to avoid. So at this point, if that happens, we go from open contact to closed contact. How do I detect the other direction? What would I have to monitor to detect the other transition? That is sort of the first guess, right? You would say a good idea would be if this C perpendicular now becomes larger than 0. But there's a bit of an issue because here I'm treating this not as a unilateral constraint, but as a full constraint that says, get this contact distance to 0 and compute your lambdas that it stays 0. So once we're here, we're basically stuck. Right? We're mathematically enforcing that my contact distance stays at 0, so it will never automatically become positive.
And we can monitor lambda, and if it's close to 0, we open the contact.
Exactly. Here on this lambda, there's also a vertical or normal component which has to be strictly positive. Because it's a unilateral constraint, ground can only push against my foot. It can never pull. Right? This wall, it can push against my fist, but it can never pull against my fist. So if I model this as a equality constraint and say that contact distance is 0, and I monitor my normal component of my contact force, if that becomes negative, I know that the ground is basically pulling on my foot, which cannot be, which means in reality I would leave the foot and transition back to the left case, to open contact. So I would have here the transition when my perpendicular contact force is equal to 0. You could do this in MATLAB, for example, in OD45. You have these event tracking capabilities. We will implement this next week. But you can look for zeros in some cases. And if a certain variable crosses a 0, your integration will stop. And if I'm basically integrating these equations of motion, I would track the 0 crossing of this variable. If I'm integrating these equations of motion, I would track a 0 crossing of this variable, and then I would always stop the integration and start basically with the other system. Now you had a question.
Sorry, about the part where you said that the open contact, the perpendicular constraint force is larger than 0, and it's equal to 0 on the close contact. Can you re-explain this?
Well, just physically, right, for a contact to remain closed, and if it's a unilateral contact, I basically have to push into the plane, right? As soon as I start pulling away, I will leave this closed contact scenario. So by just monitoring this force, right, which physically can never be negative, and here I'm actually saying I want it to be positive, right? Because if it's 0, I know I'm basically transitioning into this other case, right? As soon as this is 0, I already know I'm basically in this open contact scenario where the lambda is 0, but now I can get here a positive contact distance. And sort of the other way around here, I always say this contact distance have to be positive because as soon as it is 0, I'm transitioning into close contact. And if you're strictly speaking, right, there's somewhere in between, there's this case where the contact distance is 0 and the contact force is 0, right? And that's exactly when we do the transition.
Now, what happens when the contact distance dot is equal to 0?
In this case,
yeah, in the transition part.
This is called grazing. So it basically would mean you're moving to the contact surface, but you're not going into the surface. You're basically just moving perpendicular along the surface. So in a sense, I'm still in free space. And then I could, for example, move away. Right? It's a corner case that hardly ever shows up in an implementation, but sort of from a theoretical perspective, you want to make sure that in this case, you not already trigger the transition. Right? So you want to avoid grazing. Okay? Questions? Any other questions? Nothing of new at this point, or nothing interesting. It's just we have these two cases, and we model unilateral contact at either open or closed contact, and we have identified conditions when we switch from one to the other. Now, let me circle the problem. We explicitly said we want to have a close contact when this constraint violation velocity is negative, because I want to move into the contact plane, right? I want to ensure that I'm really getting into contact. And as soon as I'm in contact, that constraint violation velocity is 0. Right? So in free space, I can have a velocity in this direction. When the contact is closed, I cannot have a velocity in this situation. And under the assumption that is sort of the key assumption in this class, that we're all only talking about rigid bodies, right? There's no deformations or anything. It basically means that I need an instantaneous change in velocity. I'm going from open contact with some negative velocity component to close contact with a 0 velocity component in 0 time. And this is what we would call a collision, right? It is something that is not really physical, because it means velocities change in 0 time, which they can only do if you have infinite accelerations, which you can only get if you have infinite forces. So there's a bit of a modeling idea behind this that comes out of the fact that we're working with rigid bodies. Right? When I do this physically with my hand, of course, I get deformations of sort of the wobbling mass, or the soft tissue in my hand, which is being compressed, and the whole thing happens not in 0 time, but over a finite duration. And that basically means that I have large accelerations, large forces, but they're not getting infinitely large. It's just a very, in a sense, a stiff process. And we want to model that because we want to model everything as a rigid body. We will model things as being infinitely stiff. So that is going to be basically the topic of today. We will talk about collisions. Or we can also call them impacts. And the idea behind this is that with rigid bodies, we need sometimes discrete changes in velocity. And in velocity means, of course, in this contact space or constraint space velocity, which goes from some value to 0. And then, of course, also in our generalized coordinates, because there's a linear relationship between these two. So if C dot jumps, then Q dot also needs to jump. And this happens by infinite accelerations. So our C double dot becomes infinite. Our Q double dot becomes infinite. And these are caused by infinite forces. That's the problem that I want to discuss today. And I want to start with a very, very simple example of two particles that are moving in 1D. So they're just moving along straight lines, and they are colliding with each other. Colliding with each other. And if they're rigid, they will interact for a duration of 0. Which means I have to add a little bit of a new naming convention. I cannot say my velocity at time t when it comes to this instance of the collision, because everything happens in 0 time. So I will now talk about a t minus, which is the time when the collision begins, or just before the collision, and t plus, which is the time just after the collision. And that difference between these two things will ultimately go towards 0. And I will use this minus and plus convention for every other variable as well. So here I'm saying v minus velocity before the collision, v plus velocity after the collision. It turns out that in this particular case, if we zoom in, right, we're not really interested in the velocities of these two bodies, v1 and v2. The thing that we're interested in is just sort of this one-dimensional constraint space, c, and then, of course, the constrained velocity c dot and acceleration c double dot. Because I have this one-dimensional constraint space, which is just the distance between the two particles, I will also have a one-dimensional constraint force, a lambda, that will push these particles apart. And now we can look at what's happening here. So I will start with the graph over here. You see time. I show here t minus. So the instance when the collision process will begin. And until then, it's pretty clear what will happen. The bodies will move towards each other. There's no other forces acting at them, so they will move with constant velocity. The contact distance is getting smaller and smaller and smaller. This is why my c dot is negative, but there's no acceleration, so I have a constant velocity and I have a 0 acceleration. And before these two bodies are in contact, of course, there's going to be no force, so there's going to be a lambda of 0. Now, let's first think about what will happen in true physics at this point. So this is now the point where the two particles or two balls will touch each other. What will happen in real physics next? They deform, right? So I get somehow an elastic deformation, which basically means for me that this contact distance in physics actually becomes smaller, right? If I compute the distance ball center to ball center, right, it can actually get smaller than 2 times the radius because these balls somehow compress. So I get a compression here. And this compression essentially creates a deformation, and that deformation is somehow a viscoelastic process. And I can think of that as a spring damper element that creates a force that is proportional to the compression velocity and compression distance, which will mean that in this case I will get some contact force lambda. That contact force lambda is going to create an acceleration, and that acceleration is going to create a change in velocity. And now I drew everything basically until the point of maximal compression, at which point my velocity becomes 0, my acceleration, my force are all maximal. And then I get a decompression phase in which I essentially decompress. And as I decompress, my force will go back to 0. And then at this point, I will have liftoff. So I have an acceleration here. At liftoff, that acceleration will also go to 0. And that means that I'm sort of asymptotically reaching here some velocity, some final velocity, and then once the contact is open again, that final velocity is going to stay constant. So I'm drawing here a straight line. If we look at this big picture, constant velocity, the velocity changed their sign, and the magnitude of the velocity got a little bit smaller because we have energy dissipation. I don't get all the energy back, and I have the springy behavior, so I have compression, decompression. I get a change in sign, and I get a slightly smaller velocity. This is what happens physically. Now, what we can do is in our head say, what would happen if these two balls that we have are made from material that is a little bit less compliant, but otherwise has the same properties. And with same properties, I mean especially the same amount of energy dissipation. Well, what will happen is that I will have a stiffer contact, which means I get less deformation, and everything will happen quicker, right? Higher frequencies. But sort of big picture, the velocity I get afterwards, so the slope of this line is going to be the same. Sort of same in the velocity diagram. If I have a stiffer contact, things will happen quicker, but ultimately will give me the same global result, same velocity after the contact process is over. And that, of course, means, right, we need larger accelerations, and because everything is stiffer, we have larger forces, which are now acting over a shorter amount of time. So accelerations get larger, forces get larger. If I think about the area under these curves, so the integral from t minus tt plus, beginning of contact phase to end of contact phase, over my accelerations integrated against time, that I need an integrand. The integrand of c double dot is c dot, and I need to evaluate this at time t plus and time t minus. And what that is giving me is the velocity after the collision minus the velocity before the collision. So the area under this curve is simply the difference between this velocity and that velocity. And if sort of energy dissipation is independent of stiffness, I see that the area under sort of this solid curve and under the dash curve have to be the same. So that stays constant. It does not change with stiffness. The same thing can be said about the integral over my constraint force or my contact force lambda. So when I integrate lambda dt, that area is also going to be independent of the stiffness. And we will give this integral a name. We're going to call this capital lambda. Right? The integral over the constraint space accelerations is the difference in constraint space velocity, and this guy, we give this a name, we call it capital lambda. And we just saw that the amount that we get here in both cases is independent of the duration of the impact, which I will write here as t plus minus t minus. And with that, I can now make the transition into a completely rigid body. What means completely rigid body? We will get instantaneous changes in velocity. But since we want this to have sort of globally the same behavior as the physical process, which is some sort of viscoelastic process, I know what my outcome in terms of velocity is. I will immediately jump sort of to this final velocity. In terms of position, this means I get a kink. Right? I have the same terminal velocity as in the compliant case, but it happens immediately. And in terms of acceleration, I now get infinite values, right? Because my velocity jumps, my acceleration basically gets the spike. And my contact forces also become infinite. So this goes to infinity. And this goes to infinity. But even with these things going to infinity, we still know that the integral over these quantities is well defined. Right? The area under this curve, which has 0 width and infinite height, the area is well defined as this contact impulse capital lambda and the difference between these two velocities. So this capital lambda, we call this an impulse, contact impulse. In the past, we called impulse something else, right? P was an impulse. But the derivative of P was a force. So the integral over force is going to be an impulse, right? Has the same unit of Newton seconds. So this capital lambda is an impulse, and it's finite even if the forces lambda are infinite. And now this gives us a way to describe these collision processes, because sort of the key variable or the key effect here is this change in velocities. That is something that we somehow need to describe. And then everything else basically follows, right? This change in velocity gives me a kink in position, and this change in velocity gives me sort of these infinite spikes, but the change in velocity will define the area under these infinite spikes. To get the change in velocity, we need physics, right? We need to somehow model this viscoelastic process that's happening here. And the idea is basically, however you model this, you will get a change in velocity, and you get some loss of energy, right? There's some elastic behavior which will change the sign, and there's going to be some damping in there which will change the magnitude of the velocity. And you cannot just state an empirical law that says the change in velocity, or the velocity, the difference in velocity, so this is nothing else but C dot plus, is going to be minus some factor of the relative velocity before impact. This is called Newton's impact law. And this epsilon is what we will call the coefficient of restitution. And it's a measure of energy dissipation. What values of epsilon make sense?
Positive.
Has to be positive. Otherwise, we have no separation, or let's say non-negative. Otherwise, we have no separation of the particles, or they would keep intersecting each other afterwards. So it has to be positive and smaller than 1, right? Otherwise, we would get an increase in velocity, so we would basically gain energy. And the two corner cases are epsilon equals 0. This is called a fully plastic collision, where all the energy is gone. So it basically means these two particles will stick to each other after the collision. They collide and stick together. No energy that came from the deformation comes back. This is called a fully plastic collision. And then epsilon equals 1 is the opposite, where we get all the energy back. No damping, no dissipation. This would be a fully elastic collision. And this is an empirical law. Works fairly well for many materials, for many cases. But it's also very, very simple. This is why people use it. And you can imagine that in reality, things are more complicated. That this amount here, right, we say it's a constant. So it doesn't depend on the impacting velocities. And I can already give you some scenarios where this is nonlinear, right? Imagine you have two glass balls impacting. At low velocities, they're very elastic, right? So you get a coefficient of restitution, epsilon, very close to 1. Glass turns out to be a very elastic material, very little damping, so you get good energy storage or good energy return. Elastic collision. But then if I gradually increase that velocity and make it larger and larger and larger and larger, glass is also very brittle. There's going to be a point where you immediately transition to epsilon equals 0, where this glass ball will just shatter and turn into, little shreds, and you don't get a rebound, right? And of course, that's an extreme case, but showing you there may be more to this than simply saying it's always going to be epsilon, right? And you have the same when you think about other materials where you have elastic deformation, and in steel, there's at some point a plastic deformation. So at larger velocities, this might change, right? So this epsilon could be a function of this contact velocity itself, right? Can change over time, right? Physics can be much more complicated. And I think this is important here. This is a purely empirical law. One that works very well, right? And there are others. There are ideas where you say, this is a measure of velocity. If I say this is a symmetrical process, I can maybe split it into a compression phase and compute how much energy is basically used up until the compression, and then do a decompression and say you get a certain fraction of the energy back, which would be a more direct measure of energy return. And that could give you another collision model. And then we wouldn't be talking about velocities here, but we would be talking about energy. And there are other effects, right? And I mean, we can generalize this to a multidimensional case where we have not only, right, here we had a one-dimensional velocity between two bodies, but in general we have sort of this multidimensional constraint space with constraints in different directions. And here this epsilon would then, in a sense, become some sort of matrix. Yeah, so this epsilon, this could be a matrix. Yeah, in the simplest case, scaled identity. All the contacts are the same. Or a diagonal matrix. Some contacts are dissipative or more dissipative than others, but you could also think about coupling effects or things much, much more complex. And this is not part of this, right? Because of this class, because this would now deal with physics, what's physically happening, and we are talking about how can I simulate these physics. But it gives us a way to now work with, sorry, there should be a minus here, epsilon times c dot minus. We can now work with this, and we can work with this also in our generalized coordinate space, because we know that c dot is our j lambda times q dot. For rheonomic systems, there may be an additional term here, right? There would be also a g lambda partial dt, or sorry, not dt, partial t. But if I look at the difference, c dot plus minus c dot minus, that is always going to be j lambda times q dot plus minus q dot minus. So these rheonomic components in this difference would be the same, right? This happens in 0 time, so my constraints don't change. If there's a time-dependent constraint, a motor, that motor cannot move in 0 time. So this term would be the same on the left and the right, and we're basically always, also for also for rheonomic systems, we would always get a change in constraint space velocity that can be written in this form. And now we somehow have to get this into our equations of motion. And I leave a little bit of space above this and before. But I will start by writing down the equations of motion. And I'm going to resort them a little bit in the sense that I put everything on the left-hand side. So we have f and g and tau. And of course, because we're talking about a collision, we have a j lambda transpose that gets multiplied with these constraint forces. And since I moved everything, again, leave a little bit of space here, since I moved everything to the left-hand side, on the right-hand side, all I will have is a 0. Now, we already know that we will not be able to work with this equation because it contains q double dot and lambda, which will tend towards infinity. And we cannot do math with infinite values. But we know that their integral is going to remain finite. And that gives rise to the idea to simply go ahead and integrate this equation over time from t minus to t plus, integrated over time, so integrate dt. So this is the idea that we will pursue here. We integrate the equations of motion over the collision. And then we look at the limiting case where the difference between t plus and t minus approaches 0 from above. So nothing that I've written here is a physical assumption or simplification, right? I said compute this integral. I can do this, right? And if the function is 0, the integral is going to be 0. And now I look at the limit of t plus going against t minus. In that case, I know that some things will simplify. If time doesn't change, my generalized coordinates are going to be constant. Right? I have jumps here in velocities, but I don't have jumps in position. So since I let t plus go towards t minus, or the difference go towards 0, my mass matrix M and J are going to be constant, or I can treat them as constant variables. My Coriolis forces are finite, which means that the integral over them, over something finite, over 0 duration, is going to be equal to 0. The same holds for gravity. Integral over gravity is going to be 0. And the same holds for my motors. They can only produce finite torques. So the integral over these torques, and all of these should be dt. It's not the cleanest notation, but I hope you know what I mean. If I integrate over these quantities, they're all going to be 0. But the integral over q double dot is not going to be 0, right? It is going to be q dot plus minus q dot minus, the jump in velocity. And that is because the accelerations can become infinite. The integral over lambda is going to be some finite quantity that we will call capital lambda, this impulse, but it's not going to go away, right? Even in the limit of the integral, or the duration of the integral, width of the integral being 0, those still have some value. So mass matrix is constant. I can pull this out. Integral over q double dot is q dot plus minus q dot minus. Integral over f is 0, g is 0, tau is 0, minus, and I will put this on the other side of the equation, j lambda transpose, which is constant, and then the integral over lambda is going to be my impulse capital lambda. And I now have my equations of motion in the integrated form. So instead of accelerations, I'm looking at jumps and velocities, and instead of contact forces, I'm looking at a contact impulse. And now I do a bit of a manipulation where I multiply this from the left with j lambda times m inverse. I multiply this on both sides from the left. What do I get here? I get j lambda times m inverse times m times q dot minus q dot. M, those cancel, m inverse and m. So I get j lambda times q dot plus minus q dot minus. So I'm getting on the left-hand side, I'm getting this term here, which is equal to the jump in constraint space or contact space velocities, c dot plus minus c dot minus. And on the right-hand side, I get j lambda, m inverse j lambda transposed times lambda. And I give this guy here a name. I call this m lambda. And then I multiply both sides again from the left with m lambda. Sorry, I did this the other way around. This is m lambda inverse, pardon me, and I multiply from the left with m lambda. So I get m lambda times c dot plus minus c dot minus is equal to capital lambda, with m lambda being j lambda m inverse j lambda transposed and the inverse of that. and we call this the contact space or constraint space mass matrix. And you see that we did another projection. I have here my equations of motion, much simpler because they're in the integrated form and impulsive, but basically equations of motion the way we knew them expressed in generalized coordinates. Mass matrix times change in generalized velocity is some impulse in generalized coordinates, right? This J transpose times capital lambda is going to give me a generalized impulse in our generalized coordinates. So I have here my equations in Q space. If you look at this, I have the same form, but I now have everything expressed in my constraint space. Constraint space mass matrix times, not an acceleration because we integrated, but a jump in velocities in my constraint space is equal to this capital lambda, which is a force that lives in this constraint space, right? So we have yet another projection, very similar to what we've seen before, right? Where we had equations of motion in Cartesian space, and we projected them into the generalized coordinates. Now we went from the generalized coordinates into our constraint space. And we have a similar structure, right? Remember in our first projection, we had J transpose mj, J transpose times mass times J to get the components of our mass matrix. Here I have J times M inverse times J transpose, and then inverse around the whole thing. So this is kind of the reverse of this mapping, because in one case we went from Cartesian space to generalized coordinates, and here we, in a sense, we're going from generalized coordinates back to Cartesian space or different space, right? But in the other direction. There's a lot to discuss here. Conceptually, meaning of this mass matrix, but I want to stop here and pick this up on Monday. You can, on Thursday. You can imagine how this goes. Now I can use this equation, insert my impact law here, compute lambda, insert it here, and then get a new generalized velocity. That's sort of the short story. But in practice, there are a few interesting things that I don't want to miss out. Today, I want to do something else in these last 15 minutes. I want to talk about the class project. You all know that part of the exam is going to be a little project that you can work on together, but that you have to solve eventually on your own, right? You have to hand in your own solution, and you have to write a little report which has also be your own work. And this is in your best interest because the exam is heavily based on this project, and we're going to ask you things about everything that's in your implementation and everything that's in your code, in your report. So in your code and your report, and your grade is based on your answers and not what's in the code. So if you put stuff in your report that you just copied from someone else, you're basically hurting yourself, right? Because we're going to ask you about it and you have no idea, and we will just determine, okay, you didn't do this yourself. But in the lead up, of course, you can ask questions, you can talk to everyone, you can discuss this just as you would do any other exercise. In terms of volume, it's about an exercise, but it's going to be a little bit more complex because it's not template based. You will not get any template, so that requires, I think, a little bit more thinking on your side. If you look at this, this will be posted on Ilya's afterwards. There's a backstory that you can read at your own time. But basically, what we're going to do is we will model a human leg. Not in all its detail. We will simplify things quite a lot. We will, however, have to create two new joint types. We will do a hip joint, which is a ball and socket joint. That's not yet in our repository or in our library of joints. So you will have to create a ball and socket joint that allows rotation about 3 axes. Abduction, adduction, flexion, extension, and then internal rotation. This is how it would be called in an actual human leg. And that's anatomically quite accurate. And then we will model a knee joint. Knee joints are tricky because in a human leg, they're basically a mixing of sliding and rotation. We will model our knees not anatomically correct, but as the rolling contact between 2 circular surfaces. Rolling without sliding. We have a rolling contact where we have a circular object with a flat ground, and here you will have to extend this to rolling without sliding between 2 circular objects. So there we need 2 new joints. That's something you will have to do within the project. And then you have to set up a model of a leg. We actually don't give you any information on that. So, ask ChatGPT or Google what are good inertial properties, segment length. It doesn't have to be super anatomically detailed, but things like the offset, right? You have here your femur head. In a human, right, this would be the pelvis segment. I mean, we see this here, right? There's the joint, and then you have the femur head. So there's some offset between center of mass location, joint locations. You have to think about this a little bit, right? And then come up with some values, right? Do you measure your own leg to get your geometric properties? Or you go in the literature and take the 80 percentile female that you find in some table that maybe NASA has posted or something. Everyone can pick this themselves. And then with this, you will run a simulation where what you will simulate is basically this leg hanging freely back there. And then you don't apply any torque at the hip. So it just, driven by gravity, swings forward. At the same time, you will have to do some active control of your knee joint, similar to our last project with the PD controller with some additional feed forward, where the feed forward should come from some inverse dynamics routine to keep, during this falling motion, to keep your knee joint perfectly extended. And we will simulate until the toe, which is just going to be a point somewhere situated on your foot in an appropriate anatomical location where the toe hits against a wall, which is a fully rigid contact and is assumed to be frictionless. So you hit the wall, plastic collision, you come to an immediate stop, so epsilon equals 0, what we just saw, and then you can still slide left and right because it's a frictionless contact. And that's basically the final task, that you give us a simulation where you set up your model, you set up your joints, you set up some initial conditions, you run a forward simulation, you compute the collision, you compute the outcome of the collision, and then you compute sort of a little bit more of your trajectory after the collision. Okay, question?
I noticed that on the front view, the toe is on the inside of the limb. Is that significant?
You can choose it. You can basically choose. We don't on purpose because we want to see some variety of solutions, right? If we give you a problem where everyone has to do the same thing and comes up with the exact same answer, it's a little bit boring. So we want to give you some variety. Here we'd probably choose a point on the inside of the leg because that's your big toe, but you can also do small toe if you prefer that as your point of contact. Yeah, and that's a choice. And the same for all other segment dimensions, initial conditions. If you want to start here, or do you just want to do a short motion? There's a lot of freedom that we leave you in this project.
The controlling has to be after the impact active, or?
Active all the time, but of course you cannot do anything during the impact because we just saw that the integral over tau is going to be 0. So there's nothing you can do. Okay, If you read through this in detail, you will see that we give you actually a number of tasks. And this is not the order in which you should do things, but it's basically for us that you give us, for each task, we want a little segment in your report. So number one is you do the whole thing without the wall and without the knee joint. So you just do a rigid connection, just to set up the model, set up the basic simulation. But of course, you have to do your rotation, your ball and socket joint. So this is task one. Task two, you compute the collision, still with the rigid knee joint. Task three, you build a knee joint and you test it on this little scenario that we have here, where we have a fixed disc and a single segment with a single toe point, and you're basically creating a second simulation just to test your knee joint with this test case, and you validate that. Then you integrate your knee joint into the leg model. You run a simulation where you first let the torque at the knee joint be equal to 0. So when your leg falls, your knee joint is probably going to move in some way or another. And then the last task is to do basically an inverse dynamics-based controller that keeps that knee joint fixed. You can do it in another order. So, right, we haven't done collisions yet, so you can skip task 2. I would always start with this, but you can skip task 2 and then do the knee joint first, or you can even start with task 3, then do 1, then do 4, then do 5, and at the very end do the collision. Doesn't matter to us, right? But in the end, you should prepare a report on each task, and in particular, each task should produce these 4 figures, or actually not all 4 apply. Let's say those figures that apply for the task. So generalized coordinates and generalized velocities, of course, you do this in each task. Position and velocity of the toe point, you can do this in each task. Contact force as a function of time, of course, you can only do this when you do the collision. Actuator torque as a function of time, of course, you can only do this for task 5, right? This is what we want to see. What do you have to prepare? So you have to solve this, and ultimately you have to send in a main file for each task. Main 1, main 2, main 3, main 4. Those should be self-contained. They should not load anything. That's not allowed. They should do the entire computation that is necessary to produce these 4 figures, or the appropriate figures for this task, automatically. So if we run main 1, we should get the first 2 figures for the simulation, rigid leg, no wall. If we run task 3, we should get the simulation of this little test example, and so on. In your main folder, there's only going to be these 5 mains. Everything else is in subfolders. In particular, you will have a subfolder called classes, right? Just the way we have this, or a library, or however you want to call it, and it will contain all the class files that you need to solve the problem. Please also include those that we provide, coordinate system class, environment class, so that your whole thing is self-contained. And of course, you throw in your ball and joint class, and your knee joint class, and maybe other functions or classes that you would like to add, maybe something where your controller, or so on. This is where we give you absolute freedom. And then you hand this in. At the very end, you get instructions how to do this. I think we just get this by email. And then we ask you to prepare a report. Double column, 2 pages, not more. So it's very, very short. We don't want full sentences. We want bullet points, because we don't want you to feed bullet points into ChatGPT and then us feeding reports through ChatGPT to get the bullet points back. So it's just going to be bullet points, key information. What are my modeling assumptions? What are my key algorithms? How did I create the ball and socket joints? How do I define my generalized coordinates? Bam, 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 right? And then you go, task 1 works, here's my result. Task 2 works, here are the results, and so on. You already see that there's some testing built in, right? We do the rigid leg first, and then later we say we have a knee, but you have to torque it such that it behaves like a rigid leg. So you can do comparisons, report on them. 2 pages max of text and equations. If we give you a LaTeX template, so we recommend that you do all this in LaTeX. And then 4 figures, the most relevant ones, which for most of you, if you finished everything, are going to be the 4 figures produced by task 5, right, by the last problem. And then you can basically print these 4. They don't count towards the 2 pages. And then we will, you will get the report. You have to sign it, that this is your own work. You will get it during the exam. Questions so far? You have to read through this carefully. There is one thing that I should mention, and this is, you may find this initially too difficult. And if you have a problem that's very complex and you find it too difficult, a good strategy is to solve a problem that is simpler. So for example, if you say 3-dimensional ball and socket joint, that's too complicated. Let's first build a simulation that just uses a planar model and a rotational joint, right? And if you say the contact is too difficult, right? Skip task 2 and first do the other tasks. If you can't figure out the inverse dynamics controller, just use PD, right? And then either do this first and try to build up to something more difficult, or if you never get there, that's okay as well, but then mention it in your report. You say, I wasn't able to do a ball and socket joint, so instead I modeled a gimbal joint, which has just 2 degrees of freedom, but because I found it easier to assign the equations of motion there, the generalized coordinates there, or instead of a gimbal joint, I used 2 rotational joint with flip joint axis and a zero mass body in between or something. Right? There's many ideas that you can do, which is not what we intended, but which could make the problem simpler. So again, you can be very creative there, but you have to report it in your report, and then of course we will discuss this report in the exam. I think I said everything that's important. You are allowed to talk to each other. You're allowed to talk with us. We will have office hours. Iskander will post all of this to Ilyas, but Monday, 3:45 to 5:15, Thursday, 11:30 to 1 o'clock, we will have office hours down in our satellite office here on campus. So if you have any questions, if you want to discuss things with us, feel free to ask. We will not give you the solution because it's not going to help you. Right? This is not the exam. This is the preparation for the exam. Right? So the goal is not to immediately get a working solution as quickly as possible, but the goal is to understand this as well as possible so that you can defend it in your exam. Okay? Give it a read. We can discuss it again on Thursday. Have a good week. See you then. Thanks.